Many times when studying a subject, there is some pivotal point which one has to understand, and then everything builds smoothly and logically around this pivotal point. In studying carbohydrates, it seems that this pivotal point is understanding the structure of alpha-D-glucose. The chemical formula of glucose contains 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. However, it tells us practically nothing about the chemical and physical properties of glucose. It is the structure of molecules such as this, in other words, the way carbon, hydrogen, and oxygen atoms are connected among themselves, that determine the chemical and physical properties of the substance. Therefore, we'll devote some time now to some aspects of the structure of glucose. There's a lot of symbolism in chemistry, which makes it convenient to represent easily complex structures, such as that of alpha-D-glucose. Although initially confusing, once one gets used to it, this symbolism may greatly simplify getting across ideas about phenomena in chemistry and physics. This is a symbolic representation of alpha-D-glucose structure, which we're going to study now. We see that only some of the atoms participating in the structure are shown, such as some of the hydrogen atoms, oxygen atoms in hydroxy or hydroxyl groups, and 1 carbon atom at position 6. There's another oxygen atom shown explicitly here, which is a part of the so-called pyranose ring, typical for glucose. The rest of the carbon atoms are not shown explicitly. Their existence is implied at the crossing points of the short lines by which we symbolically represent chemical bonds. Notice also that some of the hydrogen atoms are not shown explicitly. We agree to accept that there are hydrogen atoms at the end of these bonds. There are some other interesting things to be observed in this structure. For instance, notice that the carbon atoms are numbered 1 through 6. Also, the position of the hydroxy groups and some of the carbon atoms determines the naming and even the very nature of the compound. Flipping over of the hydroxy group at carbon atom number 1 from bottom to top position changes the name from alpha to beta. Now we have beta D-glucose. The mirror image of this structure is called beta L-glucose. Substances in L form of their stereoisomer rotate the plane of the polarized light in a direction opposite to the direction in which their D form rotates it. Now, let's revert back to the structure of alpha-D-glucose and see what will happen if we flip over the hydroxy group at carbon atom number 4. This is the structure of a substance different from alpha-D-glucose. This is the structure of alpha-D-galactose. Alpha-D-galactose is less sweet and less soluble than glucose. This is an illustration of the fact that sometimes an ostensibly small change in the structure of a compound can have a substantial effect on the properties and the very nature of that compound. Okay, Let's go back to the structure of alpha-D glucose and observe that carbon atom number 1 is a very special carbon atom. Indeed, carbon atom number 1 has a hydroxy group attached to it, a hydrogen atom attached to it. Remember, there is a hydrogen atom residing implicitly here, a group of the type OR1, and another group which we will symbolically denote as R2. What kind of a structure was this? This is the structure of a hemiacetal. Hemiacetal is a compound that has an ether group, a hydroxy group, and a hydrogen attached to the same carbon atom. Now, how is this structure similar to the structure of glucose? They look so different. Now recall what was said at the beginning about symbolism in chemistry, and also use some imagination. Suppose R1 and R2 are connected, then a ring will be formed similar to the ring of glucose. Somewhat more symbolical though. This OR1 group is an ether group. Recall that an ether is an organic substance that has two carbon atoms connected by an oxygen bridge. In the structure of glucose, we see that there are two carbon atoms connected by an oxygen bridge. Therefore, the structure of glucose contains an ether group. Now observe the structure of glucose. Indeed, carbon atom number 1 is connected to one hydroxy group, to a hydrogen that implicitly resides here, and to an ether group, somewhat peculiar though, because this ether group is part of a ring. Also part of a ring is the group that we symbolically denoted by R2. Recall that a hemiacetal is formed by the reaction of an aldehyde with an alcohol. A hemiacetal is stable only when part of a ring, as in the case of glucose, in solid form. Let us see how this opening of the ring happens. When glucose is being dissolved in water, the bond that connects carbon 1 with the oxygen from the ring is cleaved. The hydrogen from the hydroxy group at carbon 1 moves and forms with the oxygen from the ring a hydroxy group. This is in fact an alcohol group. The remaining oxygen at carbon 1 forms a double bond. There's a hydrogen atom here, of course. We can redraw this in a more familiar form. Now we see that as a result of opening of the ring, at one end of the molecule an alcohol group is formed, while at the other end there's an aldehyde group formed. It should be noted that the aldehyde form of glucose is unstable, and as soon as it's formed, it closes back into a ring structure, either as alpha-D glucose or the stereoisomer of alpha-D glucose, beta-D glucose. Nevertheless, the fact that glucose exists part of the time as an aldehyde in water is important because it explains the reducing properties of glucose. Glucose is a reducing sugar. Not all sugars are reducing sugars. Recall that an aldehyde is oxidized by a silver-ammonia complex to form carboxylic acid. This is the ion of the carboxylic acid. And metallic silver deposited on the walls of the test tube as silver mirror. In other words, the aldehyde acts as the reducing agent towards the silver ammonia complex and reduces it to metallic silver. In the process, the aldehyde is being oxidized to carboxylic acid. This reaction is typical for aldehydes and is used to distinguish them from ketones. Most of the ketones do not have this property. Now let's go back to the structure of alpha-D-glucose and observe another important reaction, namely the reaction between glucose and another alcohol. As a result of this reaction, the so-called glucoside is formed. This reaction is important because it is a step towards understanding the formation of di- and polysaccharides. Indeed, if in place of this alcohol we have another molecule of glucose, remember that glucose, besides all other properties, has also the properties of an alcohol, then a disaccharide called maltose is formed. A molecule of water is formed as a result of this reaction. The remaining oxygen connects carbon atom number 1 from the first glucose molecule with carbon atom number 4 from the second glucose molecule and forms the so-called alpha 1, 2, 4 linkage. This alpha, of course, follows from the fact that our initial glucose was alpha-D-glucose. There are two important properties of this structure that are to be noticed. First of all, the left structure is no more a hemiacetal. Recall what the definition of hemiacetal is. Carbon atom number 1 is not connected anymore to an OH group. This, in fact, already is an acetal function. Therefore, this ring cannot be opened. It is said that this ring is locked. On the other hand, the structure on the right can be opened because this still is a hemiacetal. The conclusion is that maltose is a reducing sugar because there's a ring that can be opened and it can exist in aldehyde form. Take a look at carbon atom number 1 from the first ring structure. Carbon atom number 1 is attached to two ether groups and to a hydrogen atom. This is the structure of an acetal. Acetal in a ring structure is stable, therefore this ring will not open when maltose is dissolved in water. This ring is said to be locked. The second ring, however, will open when maltose is dissolved in water because this second ring is a hemiacetal. Indeed, carbon atom number 1 has a hydroxy group attached to it and only one ether group attached to it. Opening of this ring will take place in exactly the same way as in the already discussed case with glucose, through the cleavage of this bond between the carbon atom number 1 and the oxygen from the ring. Now we are prepared to observe some other disaccharides. For instance, lactose. As you can see, lactose consists of one ring of beta-D-galactose and a ring of alpha-D-glucose. Also, there is a beta 1,2,4 linkage. You can already understand why. Also, you can see that the ring of beta-D-galactose is locked, while the ring of the alpha-D-glucose is unlocked, for the same reasons as with the structure of maltose. Therefore, lactose is another example of a reducing sugar. This is an example of non-reducing sugar. Why this sugar is non-reducing is clear from our previous discussion. Notice that both of these rings are locked. This is sucrose, or ordinary table sugar. It consists of one ring of beta-D fructose and a ring of alpha-D glucose. Table sugar, or sucrose, is easily hydrolyzed by the enzyme invertase into beta-D fructose and alpha-D glucose in 1:1 ratio. Once we know how the disaccharide maltose is formed, it is immediately obvious how further molecules of alpha-D glucose can be added via glucoside or glycosidic linkages to form polysaccharides. Polysaccharides may contain thousands of individual glucose units in one chain. This is the molecule of the polysaccharide amylose, which is one of the two components of starch. The molecule of amylose is a long chain of alpha-D glucose units connected by alpha 1 to 4 glucoside linkages. The number of individual alpha-D glucose units in one chain may reach 2,000. The chains can be either random coil or helical. Amylopectin is the other of the two components of starch. It is also a polysaccharide, a polymer of alpha-D glucose. In a way, amylopectin is similar to amylose because it contains the same glucose-based long chains. Unlike amylose, however, amylopectin has, in addition to alpha 1 to 4 glucoside linkages, also alpha 1 to 6 glucoside linkages between the chains. There's another polysaccharide called glycogen or animal starch, which is similar to amylopectin. However, glycogen has many more alpha 1 to 6 glucoside linkages per molecule compared to amylopectin. Here's another important polysaccharide based on glucose called cellulose. Notice how similar the structure of cellulose is to that of amylose. The only difference is that in cellulose the glucoside linkages are beta 1 to 4 rather than alpha 1 to 4 as in amylose. There are various derivatives of cellulose such as nitrocellulose or cellulose acetate. This is the end of our lecture. From the discussion so far, we see that carbohydrates are polyhydroxyaldehydes or ketones, or substances that yield polyhydroxyaldehydes or ketones. In this lecture, we did not discuss some important properties of carbohydrates, such as chirality, rotation of the plane of polarized light. These are phenomena that give rise to one of the most subtle forms of stereoisomerism, the existence of enantiomers. An important property of carbohydrates is also their ability to store energy or to form supporting structures. These and other phenomena will be discussed in other lectures.